this is me building a prototype for 6 hours straight. This is slave labor to my own project. This is what the DIY and maker movements really look like. And this is an analogy for today's construction and manufacturing worlds with brute force assembly techniques. And this is exactly why I started studying how to program physical materials to build themselves. But there is another world. Today, at the micro and nanoscales, there's an unprecedented revolution happening. And this is the ability to program physical and biological materials to change shape, change properties, and even compute outside of silicon-based matter. There's even a software called CAD Nano that allows us to design three-dimensional shapes like nanorobots or drug delivery systems and use DNA to self-assemble those functional structures. But if we look at the human scale, there's massive problems that aren't being addressed by those nanoscale technologies. If we look at construction and manufacturing, there's major inefficiencies, energy consumption, and excessive labor techniques. In infrastructure, let's just take one example. Take piping. In water pipes, we have fixed capacity water pipes that have fixed flow rates, except for expensive pumps and valves. We bury them in the ground. If anything changes, the environment changes, the ground moves, or demand changes, we have to start from scratch and take them out and replace them. So I'd like to propose that we can combine those two worlds, that we can combine the world of the nanoscale, programmable, adaptive materials, and the built environment. And I don't mean automated machines. I don't just mean smart machines that replace humans, but I mean programmable materials that build themselves. And that's called self-assembly, which is a process by which disordered parts build an ordered structure through only local interaction. So what do we need if we want to do this at the human scale? We need a few simple ingredients. The first ingredient is materials and geometry, and that needs to be tightly coupled with the energy source. And you can use passive energy, so heat, shaking, pneumatics, gravity, magnetics. And then you need smartly designed interactions. And those interactions allow for error correction, and they allow the shapes to go from one state to another state. So now I'm going to show you a number of projects that we've built from one-dimensional, two-dimensional, three-dimensional, and even four-dimensional systems. So in one-dimensional systems, this is a project called the self-folding proteins. And the idea is that you take the three-dimensional structure of a protein. In this case, it's the Cranbin protein. You take the backbone, so no cross-linking, no environmental interactions, and you break that down into a series of components. And then we embed elastic. And when I throw this up into the air and catch it, it has the full three-dimensional structure of the protein, all of the intricacies. And this gives us a tangible model of the three-dimensional protein and how it folds, and all of the intricacies of the geometry. So we can study this as a physical, intuitive model. And we're also translating that into two-dimensional systems. So flat sheets that can self-fold into three-dimensional structures. In 3 dimensions, we did a project last year at TED Global with Autodesk and Arthur Olson, where we looked at autonomous parts, so individual parts not pre-connected that can come together on their own. And we built 500 of these glass beakers. They had different molecular structures inside and different colors that could be mixed and matched, and we gave them away to all the TEDsters. And so these became intuitive models to understand how molecular self-assembly works at the human scale. This is the polio virus. You shake it hard and it breaks apart, and then you shake it randomly and it starts to error correct and build the structure on its own. And this is demonstrating that through random energy, we can build non-random shapes. We even demonstrated that we can do this at a much larger scale. Last year at TED Long Beach, we built an installation that builds installations. The idea was, could we self-assemble furniture-scale objects? So we built a large rotating chamber, and people would come up and spin the chamber faster or slower, adding energy to the system and getting an intuitive understanding of how self-assembly works and how could we use this as a macro-scale construction or manufacturing techniques for products. So remember I said 4D. So today, for the first time, we're unveiling a new project, which is a collaboration with Stratasys, and it's called 4D printing. The idea behind 4D printing is that you take multi-material 3D printing, so you can deposit multiple materials, And you add a new capability, which is transformation, that right off the bed, the parts can transform from one shape to another shape directly on their own. And this is like robotics without wires or motors. So you completely print this part and it can transform into something else. We also worked with Autodesk on a software they're developing called Project Cyborg. And this allows us to simulate this self-assembly behavior and try to optimize which parts are folding when. But most importantly, we can use this same software for the design of nanoscale self-assembly systems and human-scale self-assembly systems. These are parts being printed with multi-material properties. Here's a first demonstration, a single strand dipped in water that completely self-folds on its own into the letters MIT. I'm biased. This is another part, single strand dipped in a bigger tank that self-folds into a cube, three-dimensional structure on its own, so no human interaction. And we think this is the first time that a program and transformation has been embedded directly into the materials themselves. And it also might just be the manufacturing technique that allows us to produce more adaptive infrastructure in the future. So I know you're probably thinking, okay, that's cool, but how do we use any of this stuff for the built environment? So I've started a lab at MIT, and it's called the Self-Assembly Lab. And we're dedicated to trying to develop programmable materials for the built environment. And we think there's a few key sectors that have fairly near-term applications. One of those is in extreme environments. These are scenarios where it's difficult to build, our current construction techniques don't work. It's too large, it's too dangerous, it's expensive, too many parts. And space is a great example of that. We're trying to design new scenarios for space that have fully reconfigurable and self-assembly structures that can go from highly functional systems from one to another. Let's go back to infrastructure. In infrastructure, we're working with a company out of Boston called Geosyntec, and we're developing a new paradigm for piping. Imagine if water pipes could expand or contract to change capacity or change flow rate, or maybe even undulate like peristaltics to move the water themselves. So this isn't expensive pumps or valves. This is a completely programmable and adaptive pipe on its own. So I want to remind you today of the harsh realities of assembly in our world. This is complex things built with complex parts that come together in complex ways. So I would like to invite you, from whatever industry you're from, to join us in reinventing and reimagining the world, how things come together from the nanoscale to the human scale, so that we can go from a world like this to a world that's more like this. Thank you.